Good evening, everyone. My name is Adrian Valdivia, and today I would like to speak about one of the biggest buildings existing here in the United States. First, I would like to start asking you if you are familiar with the background on this picture. If so, then you will know the name of this building. But if you are not familiar with this background, then you will learn in my presentation which building it is, its location, the type of loft existing on its structure, also the constraints and challenges, and some of the innovations it brought back on the time. And that is correct for those who knows the building. This is the Willie Tower, also known as the Sear Towers, and it is located in Chicago. The construction of this building was finished in 1973. It held the record as the tallest building globally for 25 years, standing at 1,450 feet, with 110 floors. The design was made by the architect Bruce Graham and engineer Fazlur Rahman Khan from the firm Kimore, Owning and Merrill. It was designed using cutting-edge techniques to handle the unique challenges related to the height of this building, the location, and the environmental impact. This building reflects a blend of creativity and practical engineering to make it both strong and visually striking. It also brought innovation on the construction industry. For example, the use of high-strength steel was to keep the structure lightweight but yet strong. Using less material kept costs down while still achieving the strength needed to withstand the wind loads and the great height that the building achieved. Also, the use of double-deck elevator was relatively new by the time, meaning that this double-deck elevator was used to increase the efficiency of vertical transportation and minimize the required space for elevator shaft. Additionally, they used thermal expansion joints. Given the Chicago seasonal temperature shift, these expansion joints were incorporated to allow the structure to adapt without cracking or warping on the temperature-related stresses. Additionally, they used the bonded turbo system developed by Fazlur Khan. It was revolutionary. It allows the tall buildings to be lighter, more flexible, and more cost-effective. The design consists of 9 square tubes, each independently stable, which collectively support the entire structure. This configuration provides the necessary wind resistance without requiring excessive amount of material. We can see that on the left hand of this presentation. They use, for example, the blue towers, the green towers, yellow towers, and the red towers. All combined create 9 tubes. Now, having this on mind, we can determine or analyze the type of loads existing on the structure of this building. For example, the load. The combined weight of this building material, such as the concrete, the steel, the glass, and the equipment, which the structure must support all the time. We can see that, for example, with the yellow arrows. The live load. This includes the variable weights like the occupancy of people, the office furniture, equipment, which can fluctuate based on the usage. One of the examples that I would like to have on mind is the pictures at the beginning, which is basically people that visit this place. So that's an example of the live load. The wind load. Chicago is known as the windy city, and such. The tower faces extremely wind forces. The bonded tube design helped there to resist these lateral forces by dispersing the pressure throughout the 9 interconnected columns. On this image we can see, for example, the white arrows pushing the building to one side. But actually the wind load is felt or is present on all sides of the building, depending on the direction of the wind. Even though Chicago is not a high risk for earthquake zone, the building is also flexible to resist the seismic load, and the tube structure helped to withstand minor seismic activity. Now, analyzing this temperature load, even though it's not a load, let's say we can present the snow load as part of the load, maybe, or we can use the temperature load as analyzing how this will create a stress on the structure. So the extreme seasonal temperature variations in Chicago can cause the expansion and contraction of these building materials. Especially these joints and materials that we use to accommodate this natural shifting without causing structural damage, and thus where the innovation of thermal expansion joints comes to life. Now that we understand the characteristics of this building, let's talk about the constraints and challenges it faced during the construction. Something positive that we can say is the budget and the time. Sears, Roebuck, and Seal, the owners of this building, they wanted to build the world's tallest building within a set of a budget. Of course, everyone wants that. Also, they aim to complete the project within a relative short time frame to move its operations into their new headquarters. So, speaking about the budget, the bonded tube system was not only structural innovative but also cost efficient. So it reduced the amount of the steel needed without compromising the strength. So that was something positive. Also, the time, the use of prefabricated steel actually was steel modules. It helped the streamlined construction, allowing multiple parts of the structure to be assembled at the same time. Now, the tower was constructed in Chicago busy downtown area. Everyone knows how these areas get busy or crowded. So the construction team managed to space by assembling steel beams off-site and transporting these steel beams during the non-peak hours to minimize the disruption in the city. Also, they used noise control to avoid or to respect the nearby business and residents. Another constraint or the challenge that they faced was about the natural elements, such as the winds. To address Chicago's strong winds, the bonded tube system was specifically designed to resist lateral forces. So these engineers conducted extensive wind-tuned testing, adjusting the design to achieve a balance between flexibility and stability. Now, speaking about the weather, Chicago experiences wide temperature fluctuations, from hot summers to freezing winters. This impacts construction materials and scale. Everyone knows that part. Now, the construction team used thermal expansion joints to accommodate the building as we explained before. This ensured the long-term structural stability of the building. So that was something very important as for the, let's say, the durability or the capability to withhold the stress of that causes these temperature changes. So the work schedules were also adjusted to account the weather conditions. So as freezing temperatures that can affect the concrete curing and other processes. So these natural elements, in my opinion, was one of the biggest challenges that this construction team faced. Besides these constraining challenges, this building became an iconic feature of the Chicago skyline and also a major tourist attraction, especially with the sky deck on the 103rd floor. Also this building, or actually the bonder tube system, which was pioneered this tower, it became a standard for designing other super tall buildings. One of the examples is the development of the Patrona Towers, located in Malaysia, also the Jimao Tower in China. In summary, the Willis Tower stands as a prime example of how engineering creativity can overcome substantial physical and environmental challenges, setting the stage for future skyscrapers around the world. Its combination of innovative structural design and efficient construction management techniques has allowed it to remain one of the most iconic and enduring structures in modern architecture. I hope you have liked my presentation, and if you have any questions, you can write me to my student email presented here in this slide. Have a great rest of your evening, and thank you very much for hearing my speech.